Okay, cool. So now let's talk about emerging memory technologies. We briefly touched upon it earlier, but I want to give you at least my personal story in this. There's a lot of work in this. There's a lot of speculative work in this. There's a lot of work that's going on here in this topic also. And I find it fascinating. And there's no way I'm going to cover all of that work that's out there, because there's just too much, and it's hard to actually follow all of that work also. But this is an important area that that people should be investing in and focusing on, even though some people may say, oh, this will never happen, right? That's good. Let people say that, and you can make it happen. Okay, this is a picture that I showed you over here, and we're going to look at the main memory technology, especially. So the problem with DRAM is, as you know, that reliable sensing becomes difficult as charge storage unit size reduces. It's fundamentally charge-based, and charge is not easy to scale. I think actually the flash memory is a very interesting example. When people were scaling planar flash memory and they were chopping the voltage range into really small pieces, people were counting how many electrons could fit into that voltage range. And if you're counting the electrons, then maybe you're fundamentally unreliable, right? That's interesting. So as I discussed, there are two solution directions, new memory architectures, which would be followed. And we've discussed some papers. And this is what we're going to talk about now. There are some memory technologies that are more scalable than DRAM, and they happen to be resistive. And they're also non-volatile. An example that I gave you is phase change memory. It's really old technology. You store data by changing the phase of material, and you read data by detecting material's resistance. We're going to go into a little bit more about that. And it's expected to be denser than DRAM because you can actually chop up that resistance range to store multiple bits per cell, just like we saw with flash. I'm going to get into that a little bit more. The problem is, this is one example. There are multiple examples. I'm going to spend more time on phase change memory because I understand this better. I don't understand other stuff as well, like memristors or RAM. So I'll leave it to the expert to talk about those. But I don't take sides. I think all of these are really interesting to examine for sure. The problem is all of these technologies, as far as I know, have shortcomings, and some of them have many shortcomings. The key question is, can we somehow enable them to replace, augment, or even surpass DRAM? I'm going to cover some things over here. So this is what's fundamental, I think. Basically, charge versus resistive memories. In DRAM and flash, you write data by capturing charge. You read data by detecting voltage. In resistive memories, you write data by pulsing some current, and you read data by detecting resistance. How do you do that? Depends on the technology, depends on the read device. Even a single technology has many, many different read devices. That's not the subject of this course, and I don't even know exactly how all of those read devices are built. And that's really very interesting also. And those read devices have enabled some of these memories. I'm going to give very broad strokes over here and then focus on phase change memory and then maybe talk about STT-MRAM a little bit more. So basically, in phase change memory, you inject current to change the phase of material. And resistance of the material changes based on that. And it's determined by the phase. In STT-MRAM, you inject current to change the polarity of a magnet compared to some reference magnet. And resistance is determined by the polarity compared to that reference. In this very broad stroke over here, you inject current in memristors, RAM, RAM to change some sort of atomic structure. And resistance is determined by atom distance and that atomic structure. Right? So let's focus on phase change memory, because when we first started looking at this, now more than 10 years ago, this was very interesting to us. And I believe this is very interesting still. I think Intel has 3D X-point. I don't think Intel has ever explicitly acknowledged that this is phase change memory, but there is a lot of circumstantial evidence that this may be phase change memory. I don't know. If it is, that's good. If it's not, that's also good. But let's take a look at phase change memory, because I think this is an interesting technology. So basically, you have some phase change material. This is one example, chalcogenide glass, that exists in two states. It's amorphous, and the states are amorphous and crystalline. And these states are very different in terms of their nature. Basically, amorphous state has low optical reflexivity and high electrical resistivity. Crystalline state has high optical reflexivity and low electrical resistivity. Which means that you can actually build a read device that can distinguish between the two different forms, reflexivities, or two different resistivities. Right? So which means that you can build two different read devices perhaps, right? And actually this technology has been around since 1960s, at least known since 1960s. And it's been used in rewritable CDs. And in rewritable CDs, the medium to read and write is optical, basically. But that's a very slow reading and writing process. It's not fit for main memory. If your main memory was like a rewritable CD, that would be very long latency. So people have developed these read devices that could actually detect the resistivities in a much faster and reliable way. And that's why this has become more interesting in, let's say, early 2000s or so. IBM did a lot of work in this area, certainly. And there are a lot of interesting papers related to this at the lower level. So the material looks like this. Basically, you have this material, phase change material, and you have a heater. And you use the heater to change the phase of the material. That's essentially it. And you encode high resistance, one phase with 0 and the other phase with 1. And you can switch the PCM cell, phase change memory cell, between states reliably and quickly. So how do you change the phase? Basically, you see this sort of diagrams in general. If you want to write, you change the phase via injecting current. And if you want to set the cell or reset the cell, you do different things. If you want to set the cell, you sustain the current to heat the cell above some crystallization temperature, like this. And if you want to reset the cell, you heat the cell very quickly above the melting temperature and quench it very quickly also. That way you can store a 1 and 0, as you can see. And to read, you detect phase via material resistance, amorphous versus crystalline. And people have pictures of this. These are manufactured. And there's a huge range between the resistances of these different states. This is the set state, and this is the reset state. You can see that the different resistances. One of the issues is, of course, temperatures are very high. So you're maybe limited by how your write bandwidth in these cases, and you may be limited by power in terms of how fast you can write. So writes are a problem in this technology, as we will discuss. Okay, so that's about the lowest level I will get. So opportunity, I think, at the architectural level is this has some advantages. So it turns out it scales better than flash. It requires current pulses, which scale linearly with feature size. And this number I've already updated last time I talked about it. This is actually around 3 nanometers right now. And it was prototyped as early as 2008 by IBM at 20 nanometers. And this is a really very nice paper about phase change memory that was published at IBM Journal of Research and Development if you're interested in learning more about the technology. It can be denser than DRAM because you can store multiple bits per cell due to the large resistance range. And as early as 2008, there were prototypes with 2 bits per cell. And this slide's relatively old, as you can see. There are already prototypes with 4 bits per cell. It's non-volatile. It can retain data for more than 10 years at 85 degrees Celsius. It's actually better than flash, I think, in terms of non-volatility. And there's no refresh that's needed, low idle power. We may get back to that. Okay, so this is the cell. This is what I showed over here yesterday. Basically, you can chop up the resistance range into 2, and you get 1 bit per cell. Or you can chop it up to, you can chop it up to 4 things over here, and you get 2 bits per cell. Now, the reading process, actually, if you have multi-level cell, it's always slower to read. Single-level cell is faster to read because you distinguish with 1 reference. If you have multi-level cell, you need to distinguish between 2 references. Actually, you first read this part to detect whether the most significant is the 1 or 0, or vice versa, one of those. Yes. Here you have 1 over here, and here you have 0. And then after that, you distinguish between the least significant bit. So it takes longer to access. And you have less margin between values, which means that your reliability reduces, and you need more precise sensing and modification of cell contents, very similar to the flash, basically. And you get higher latency and energy for reads and writes when you go to multi-level cell phase change memory. But you get higher capacity. That's the upside. Very similar to flash. So we actually, when we first started doing this, I'll give you the historical perspective from my personal perspective. We started this actually when I was at Microsoft Research. We were very interested in all kinds of memory. And this was, we knew that DRAM was not going to scale at some point in the future. And we wanted to look at some promising technologies. And this is the state of the art around 2008 or so. This is all report in the paper that was published in 2009. Basically, we surveyed prototypes that were published in low-level conferences that were published in between 2003 and 2008. And we tried to derive phase change memory parameters for a feature size of 90 nanometers. It's big, of course, but this is also 2008. And also, I'd like to point this out because this is not an easy study to do. I'll show you a graph that basically looks at all of the papers, well, a subset of the papers that we've studied that shows that you don't know enough information about this technology. But it's really important to do this kind of research, in my opinion, because this is how you can enable technology. And clearly, this technology hasn't been enabled in the last, I don't know, 10 years or so, right? But hopefully, Intel comes up with their DIMM that actually, the 3DX point DIMM that is non-volatile. It may or may not be phase change memory, and it's going to be a technology that's very similar to what we envisioned about 10 years ago. Okay, so, but 10 years ago, you don't even have a lot of prototypes. And if you look at the prototypes, they're all different from each other. This is one of the tables. You don't need to read everything over here. But these are parameters of the technology, phase change memory technology. And these are different papers that are published, that published those parameters. And no one published this complete set of parameters except for this one over here. But that's the difficulty of doing research in a new technology. You can see that this is over 2003 to 2008, and then some things are really not published. So this is, let's pick one over here. Material is usually published. That's good. These are usually small array sizes, as you can see, in terms of megabytes. The biggest one is 512 over here, which is good. But there are a lot of small ones also. And you can see that read time is not even reported in some of the studies. And when it's reported, there's some variance. This is 70 over here. This is 55. So that's not that bad. If you actually look at the set time, there's a lot of variance over here. 400 here, 100 here. So how do you actually determine the parameters? It's good to sweep parameters, of course, when you were doing simulations. But we actually wanted to determine a set of parameters for phase change memory. And you can also here see this is write endurance over here for a multi-level cell. Some studies report as low as 10 to the 4, I think, over here. And some studies report 10 to the 9. Basically, a cell dies after 10 to the 4 writes, according to this paper. A cell dies after 10 to the 9 writes, according to this paper. Which one do you trust? I guess we'll see.
The same technology specific?
For all of these are different phase change memory prototypes, but the material may be different. Although in this case, the material was the same. If you look over here, GST, ND, GS, yeah, it's a bit different. Yeah, material was different.
No, it's different type of device.
Slightly different. It's not, the fundamental principle is the same. It's just the material they use is slightly different. But some of them are not even different type of device, right? If you look over here, these are all GSTs, and there are some differences. Okay. Anyway, basically, I show this because it's really good to do this sort of study, but there are challenges in doing this sort of study also. With DRAM, we don't understand enough, but we have these devices at least. We can reverse engineer and discover, even though there are challenges. Here, we don't even have these devices. We didn't have access to any of this. Some people who report some of these papers are from Samsung, for example. Some of these papers are from Micron. Some of them are academic. They had the prototypes, but they don't necessarily report everything. And what they report, there's also a mismatch in terms of what they report. When they, for example, say latency, some of them take into account the array latency. Some of them don't take into account the array latency. Some of them are cell-based. Some of them are sub-array latency. So there's a lot of variation when you're dealing with a technology that doesn't really exist out there. Certainly, there were no phase change memory chips out there that we could get our hands on. And that's still true. That hasn't changed. Okay, so now let's try to make sense of all of these parameters. So if you look at the phase change memory properties in terms of latency, this is where it sits. This is the grand scheme of memory technologies that exist: SRAM, embedded DRAM, DRAM, flash, hard drive. And this is the relative latency in terms of processor cycles for a 4 gigahertz processor, assuming some latency. So SRAM is, of course, very close to the processor. Embedded DRAM is in this order. DRAM is in this order, let's say 500 cycles or so. So phase change memory is very close to DRAM, basically. It's much faster than flash. Flash is over here. And hard drive is orders of magnitude to the right. So This is why this technology is interesting, because it could be a contender for DRAM, as you can see, in terms of latency. And that's the first important thing. In terms of capacity, we already said that it's much more scalable than DRAM. We're going to look at that also. So unfortunately, latency is close, but not the same. So it's usually worse than DRAM. And when we looked at it, we said it's about 4x the latency of DRAM, but it's much better than flash, so it could be a DRAM replacement. So write latencies, there's heterogeneity in terms of latencies, read and write. Because for writes, actually, when you're setting, you really need to melt the material, as we've discussed, right? Basically, you need to increase the temperature significantly, and that takes a long time. And the write latency we expected is about 12x of DRAM. And this is the write bandwidth, so it's very low. Because you actually draw a lot of power when you're doing the writes. But flash, we thought it was more comparable with flash. It's good to do these studies again, I think, at this point. This is all 10 years old. But I think even 10 years old shows significant potential in terms of potential DRAM replacement for this technology. So energy is actually not good news. So I show you all reds over here, right? The red means not so good compared to DRAM. So energy, the read energy is about 2x of DRAM. Write energy is much higher, about 40x times DRAM. Energy is similar to flash. Endurance, based on what we saw, we basically said you can do 10 to the 8 writes per cell. I think this is reasonable. Some people claim that they can go up to 10 to the 12 today. We don't know. It remains to be seen. But basically, in endurance, if you do a write, you need to induce phase change at 650 degrees Celsius. This may have changed over time. But you need to go up to very high temperatures. And as a result, the contacts degrade from thermal expansion and contraction. As a result, you cannot do many of these writes. That's why the cell wears out over time. And yeah. The biggest good news at that time was really the cell size. Because cell size, we expected to scale much faster than DRAM. And that was actually, I believe this is still true. It will scale much better than DRAM. So you actually get better scaling. OK, so let's summarize even at a higher level. Question?
Yes, by mean of scaling, you said yesterday that for DRAM, the sense amplifier is almost 1 over times bigger than a cell. What is the proportion here?
Yeah, that's a good question. Actually, in current technology, I don't know. It's still pretty large. But I don't know, actually. I don't know the exact answer. It'd be good to do that study. That's a very good point. Any other questions? Yes?
What is going to be the cost per bit trained for this?
Oh, I don't know. So cost per bit, I think cost per bit will relate to scaling, right? If you can put more cells, many, many more cells per area compared to DRAM, assuming everything else is equal, your cost per bit should be lower, right? The key question is, how do you make everything else equal, right? DRAM is a technology behind which you have 50 years. This is a technology behind which you don't have 50 years. Yes, you have 50 years in terms of the material, but it's used for a completely different purpose. It was never meant to be memory technology. So cost per bit will change according to the investment you make, according to the development of the manufacturing technology. So it's not an easy question to answer. But if you just look at number of bits you can store in a given area, that looks very good. Yes? Yeah. So I think basically it does and it doesn't. We should be focused on everything. I think research should. Yeah.
Not great. It's getting quite a bit worse.
So research.
For not a lot.
Yeah. Well, we'll see. Basically, we'd like to overcome these reds as much as possible.
Okay.
And then we're going to develop techniques to overcome those reds, to enable a new technology. Because there are other benefits like non-volatility over here that could enable something that DRAM cannot enable ever, right?
Okay.
Yeah. But I think I'll take you the question a different way. That's one answer which you're satisfied with. the other answer is basically research should have no boundaries, in the sense that yes, if a technology looks like this, it may be very non-promising, but maybe we can enable it in some way, right?
Heterogeneity will solve that.
Say it again?
Heterogeneity.
Heterogeneity, yeah, exactly. Basically, heterogeneity. So maybe you can come up with some techniques to reduce the latency also, actually. So it applies, it's fair game to do it for phase change memory as well. It says what? Oh, the internet says. Yeah, I mean, there's a lot of, I don't know if Intel ever officially acknowledged Optane as PCM. So I cannot say that, but certainly there is a lot of work that built up into something like Optane. And you can see the trail of publications and things like that. So there's a lot of circumstantial evidence, but circumstantial evidence is not evidence. It's not real evidence, right? Okay. But I think it's, I'd like to believe that it's PCM, of course, because it's something that we've looked at for a long time. But of course, if it's something else, that's also very, very interesting, right? Okay, so what we're talking about is 3D X-Point. 3D X-Point is Intel's different non-volatile memory solution. And there's an Optane SSD drive that Intel has, which uses 3D X-Point as a competitor to Flash at this point. I'm not sure if it's very close to Flash. It's very interesting. It's a storage technology. But Intel is supposed to release a memory version of this technology. And
I think it's already there for samples.
samples, yes, but I think they're supposed to officially release it to the market next year, the DIMMs. Now that becomes very interesting. That becomes exactly what we're talking about right now. And if it's phase change memory, then I'd be curious how our projections 10 years ago match the real characteristics of the released DIMM. We'll see. These were not projections, by the way. These were what we thought would be at that point in time. So we'll see. OK, so let's pull back. And these are basically the high-level pros, advantages over DRAM. Better technology scaling, better capacity and cost. Non-volatility, we're going to get back to non-volatility. Basically, every cell is persistent. You plug the power off, the data stays there. That's great. In DRAM, you don't have that. And on top of this, you have low idle power because you don't need to refresh it. So you could take advantage of all of these. The cons are a bit unfortunate. You get higher latencies, especially write latencies are much higher, but read latencies are also 4x higher, according to what we thought at the time. You get higher active energy, especially write latencies are very high, and read latencies are also high, but 2x. A lower endurance, a cell dies after some number of writes. And reliability issues that I'm not going to actually talk a lot about, because there are reliability issues with any technology, and emerging memory technologies, if you focus too much on reliability issues, then you will never enable it in the system. So certainly some of these need to be solved, but one of the issues is resistance drift, meaning that I said here no refresh, but just like charge gets lost, meaning charge leaks, resistance also drifts over time. Now the time span of resistance drift is much larger than time span of charge loss, so the refresh that you need to do over here is actually at much larger time scales, but you still need to do refresh. But we know that you need to do refresh in Flash also. Flash is technically non-volatile, right? But that's not true. Okay, so basically there are challenges. If you want to enable this sort of technology to replace DRAM very aggressively, or help DRAM somehow, you need to mitigate its shortcomings and find the right way to place phase change memory in the system. And this was our picture from 2008, basically. Basically, we were thinking, OK, this is the current technology. Over time, you would move to these hybrid technologies, some DRAM, some PCM. Take this with a grain of salt. It doesn't necessarily be hanging on off the same bus. This is just pictorial. You may need different buses, and I think you do need different buses. And over time, we would enable something like this. Basically, all of memory will be replaced with PCM somehow. Then how do you do that? So this is actually, we're going to get back to this because this may be very difficult to do with at least this technology, with phase change memory technology. So hybrid phase change memory DRAM, how do you partition and migrate data between phase change memory and DRAM? We discussed this briefly, but we're going to look more into this hybrid memory solution. This one is very interesting. It was very interesting for us. We were too aggressive, maybe. Basically, we said, how do you design the entire hierarchy and maybe the cores to overcome the shortcomings of phase change memory? So we're going to examine this solution So what we did, essentially, our initial study was targeted toward that solution. As we say over here, you want to architect phase change memory as a scalable DRAM alternative. And these were the values that we assumed based on our analysis. So we assumed it's denser than DRAM. We assumed, but we're not going to use capacity in our evaluations. We're going to assume equal capacity. I'm going to show you later some evaluations that are done by others that assume phase change memory is 4x denser than DRAM, and as a result, you get much better system-level benefits. Our evaluations are a little bit more pessimistic for the phase change memory technology because we assume capacity is equal, and these are the different parameters in terms of latency, energy, and endurance. Basically, we model all of these in the evaluations, and we have worse latencies, worse energy, and clearly worse endurance compared to DRAM. DRAM endurance we assumed is infinite. That remains to be seen, but it's very hard to do those studies to figure out whether DRAM wears out or not. Okay, so this is, in one slide, what we found. Basically, if you replace DRAM with phase change memory in a reasonable system of the day, you have 4 cores, 4 megabyte L2, and organize phase change memory exactly the same as DRAM. Row buffers, banks, peripherals, everything's the same. Basically, you have a DRAM-based system, you magically replace every single DRAM cell with a PCM cell and change the parameters like what we've discussed. You can easily do that in simulation. And you use some workloads to evaluate. Maybe these are not the best workloads. Some of them are intensive. Some of them are not so intensive. A lot of them are scientific workloads, actually. The performance degradation you get is about 60%, which is a lot. And your energy increases by 120%, which is a lot. And your memory dies after 500 hours because there are a lot of writes, right? And you're doing writes very quickly to your memory. So that's a terrible solution, right, if you actually do this. And you can see that in, this is the endurance over here. How many years can your memory endure? And nothing is below 0.2, as you can see over here. So it's not good. So this technology is not good, so you need to do something about it. So what did we do? These were actually very small solutions. We're going to talk about bigger solutions. But basically, if you have a technology like this, you don't want to write to it, first of all, because writes are extremely expensive, and writes actually cause endurance issues. And you want to minimize the reads from it also, which is interesting, right? So what do? You do a lot of buffering around it. So we wanted to, the paper actually has some detail over here. If you look at DRAM, you need to have these sense amplifiers, right? DRAM reads are destructive. In phase change memory, you can organize the sense amplifiers in a different way. Reads are not destructive, first of all. So you can actually sense only a part of what you're reading. You don't need to sense the entire row in the system. So you can organize it in a different way. So what we did was basically we organized the same sense amplifiers using multiple narrow row buffers in each PCM chip. If you do that now, you can actually have a cache of multiple rows, maybe smaller rows, and that leads to better endurance, latency, and energy. You can read the paper for more detail. And we tried to be equal area in terms of this peripheral area because we're assuming everything's equal area. Again, maybe that's very conservative because this technology is different and it may actually have more area for these peripheral structures potentially, right? But we want it to be conservative. Okay. And the second idea is very simple. If you have a technology that doesn't like writes, you don't want to write into it. So you minimize the writes. You write into the area at cache block or word granularity. You don't write an entire row back. Actually, you want to write maybe only the bits that have changed. Samsung had a prototype PCM chip after we published our paper. They revealed that they have an internal comparator in their PCM chip where they actually check every bit and only write the bits that have changed compared to the previous value. So they did a read and then write after that. Read, compare, write. So, which makes sense, I think. Relatively small ideas, but this actually gained a lot of performance and endurance for us. So this is what we got after doing these tricks, a few of these tricks like this. Basically, we reduced the performance degradation to only 20%, which is still high. I say only, but 20% performance degradation is not good in general. We reduced the energy to be on par with DRAM. Take this with a grain of salt. I don't trust necessarily these power models, but it is what it is. It's smaller than 2.2x. And the average lifetime increased to 5.6 years as opposed to $500, so which is good. And we hope that scaling improves energy, endurance, and density. Now, there are caveats here. I don't think this is a good solution still, even if you reorganize everything in your DRAM chip, the PCM chip. Basically, worst case lifetime is much shorter. There are no guarantees. There are some applications that actually still kill your memory within a year or so. Not good. And also, this could open up yourself to attack, right? Some malicious application can actually destroy your memory by attacking with a write, and other people have looked at that. And the second is memory-intensive applications actually see much larger performance and energy hits. So even though average is 20%, some applications lose performance by about 60%. So that's not good. And the third one, maybe we use optimistic PCM parameters in terms of energy, in terms of energy modeling. Maybe we missed some things. I mean, this is not the perfect energy model that we have. As you see, that we don't even have a good energy model for DRAM. How do we have a good energy model for something that doesn't even exist, right? So that's the difficulty. But the relative trend is that if you do this, you can get better energy, and you get rid of refresh also. So I don't think this is a good solution. Replacing DRAM completely with technology with this sort of parameters is not going to work, in my opinion. But we did examine that solution very heavily. And we did write several papers related to this. If you're interested, you can take a look at it. I haven't decided about the third paper. Maybe this will be one of the papers, but I'm not sure yet. We're going to get back to this. Basically, I said it's not a good solution. So what's a good solution? Well, maybe you don't replace all of your DRAM with phase change memory, right? Maybe you still keep some amount of DRAM and a lot of PCM, and use DRAM as a buffer for PCM. And that can actually enable a much more scalable system, right? Okay. So we were examining some other technologies also. STT-MRAM is another interesting one. I think this is really interesting because it could affect main memory. Actually, some people thought, even before we started looking at it, some people were thinking, oh, maybe this is the best technology ever. Sometimes people come up and say, oh, I have the best technology that's good at everything. And STT-MRAM was at some point thought as the universal memory technology that's good at everything by some people. I never believed it. And if someone tells you that, I would recommend that you don't believe it also. And it turns out that's not true also. But it's very interesting, certainly, as a technology. Basically, how does it work? It's a magnetic memory. You have this magnetic tunnel junction device, which consists of a structure that looks like this. We're not going to go into the lower levels of this. But basically, you have two layers, two magnets. Imagine two magnets. One is a reference layer. You fix the magnet, its orientation. And you have a barrier, and then you have a free layer over here. And the free layer can be parallel to the reference layer in terms of magnetic orientation, or anti-parallel to the reference layer. And that's how you encode a 0 or 1. Now you have different resistance between this. This is low resistance, this is high resistance. As a result, you have a read device that can detect that low or high resistance. So if you want to write to this, you push large current through this magnetic tunnel junction device to change the orientation of the free layer. And that may not be easy. As a result, you get write errors in these devices. And you have a lot of write disturbance in this device, for example. That's true for PCM also, actually. But we didn't talk about the reliability. That's OK. And for reading, you sense the current flow. And there are a lot of papers before our paper. But our paper was the first to examine this as a scalable memory alternative, main memory alternative. So let's look at the pros and cons of this. Pros are very similar, actually, to PCM. Pros over DRAM. You get better technology scaling. It's non-volatile, low idle power. It's the same. Cons are actually better than PCM, with a caveat that I will. Actually, the caveat is over here. You don't really have a read latency problem compared to DRAM. Write latencies are higher, though. You don't have a read energy problem compared to DRAM. Write energy is higher, which is easier to deal with, clearly, right? Unfortunately, you have poor density. The size of the cell is very large today. So arguably, this is not a good match for DRAM technology. But if the technology scales well, it may be a good match for replacing DRAM. So a lot of people actually were looking at how to use STT-MRAM as a cache replacement, L2 cache replacement, for example, or L3 cache replacement, because the size of the cell is actually around the size of the cell that you have in L2, L3, L4 caches. But I think we wanted to be more aggressive, look more into the future. If this technology scales, at some point, the size of the cell can actually surpass the size of a DRAM cell. And reliability is always a question. As I said, there are reliability issues. So there's no endurance issue, actually, in this technology. As far as, again, we predicted at the time. That still remains to be seen. That's why I reserve the right to have endurance underneath reliability also, because there may be endurance issues here also. But it's not as bad as phase change memory, for sure. Because the writing process is not as disruptive. In phase change memory, when you write, you really need to go to very high temperatures to melt the material. Here, as I said, when you write, you're really not changing the temperature. When you're writing, you're injecting, yes, high amounts of current through this device, but just current injection. Yes, it increases temperature a little bit, but you don't need to melt some material over here. That's why I think this is more interesting. Maybe it's not as small as we would like to make it today. So that's why the cons are actually lower here. That's why it was very interesting for us to examine as a main memory alternative. And this also has another level of freedom, which is very, very interesting. This actually exists in phase change memory to some extent, too. You can trade off non-volatility for lower write latency and energy. Basically, you can say, oh, I don't want to make it completely non-volatile. Maybe I refresh it every 10 days or so. And that leads to a write latency that's much lower, maybe on par with reads. Now that becomes very interesting. Now you're getting even closer to DRAM, right? We didn't exploit this trade-off, actually. This trade-off is dependent on the size of the magnetic tunnel junction device. If it is very large, you get non-volatility. If it's smaller, you reduce your non-volatility. So there's a lot of interesting games you can play over here. You cannot play them dynamically, as far as I know, but you could create heterogeneous regions of STT-MRAM. Some of them may be non-volatile, some of them may be volatile. So there's a lot of design space that you can explore, a lot of architectural ideas that you can explore over here with this level of freedom, I think, that we didn't explore. We just wanted to do something similar to what we did for phase change memory, and we wanted to see the results. Basically, it's very similar. We have 4 cores, 4 GB main memory. We use multi-program workloads, very similar infrastructure, just similar to the paper that I just described. And we actually incorporated mechanisms. That's why it's called architected. We incorporated mechanisms that try to minimize writes into the array of STT-MRAM. And these are the results that we got. Basically, this is the performance loss compared to DRAM. It's only about 6%. And again, take this with a grain of salt. The energy savings is about 60% compared to DRAM. I don't believe the 60% fully, because our energy models, but maybe it's overshoots in terms of refresh. It thinks the refresh energy is very high. But 60%, it's still better than DRAM, basically, in terms of energy. So this seems much more promising, as you can see from my perspective, compared to PCM, with the big caveat that the cell size is huge right now. So you don't get, in the same area, you would put much higher capacity DRAM compared to STT-MRAM today. But who knows what happens 15 years down the road, right? This actually may scale very well. And these chips actually exist. There are companies that sell. Everspin, for example, has, I think, reasonably large STT-MRAM chips, although I think they release it very carefully into the market, so I don't know what they are.
Do the 3D techniques stacking apply to those or not?
In the existing chips or these? Yeah. I think fundamentally, yeah, you could apply to them, yes. And I believe that's what Intel is doing. But I'm not sure. Yeah. So I think fundamentally there's no, they could apply to these. Yes?
Yeah, but related to that, but if the energy, the power is right, you also want to think about cooling, right?
Sure.
So current, the way we organize the memories, we focus more on the cooling of the processor.
Mm-hmm.
And less, so do you have any comments on the cooling part?
Yeah, I mean, if the temperature is high, you need to cool the memories for sure, yes. I think this goes back to similar comments that we had with processing in memory. If your energy increases for whatever reason in your main memory, you need to have a cooling infrastructure to cool the memory also. But I think we know cooling from processors, so I'm not as worried about that. Yes?
Have you ever checked this result with Everspin technology?
I mean, I would like to take their chipset and do the same studies, but we haven't checked that, no. Yeah, some of these companies that are doing these technologies don't like talking. And I understand some partially, I don't understand fully. Because they can benefit from validation of some of these. Because I think that's a really good result for the technology. 6% is not bad. That's almost within the DRAM, right? Of course, in this case, we're not taking into account capacity issues. Again, we're assuming equal capacity. And at this point in time, I think that's favoring STT-MRAM. Because I don't think you can have equal capacity at the same cost with STT-MRAM to DRAM. But with phase change memory, we may be favoring DRAM by assuming equal capacity. Okay, so if you're interested, that's the paper. There's more to do in this area, I think. So I think even if it's STT-MRAM, a more viable approach is something like this. Certainly, if your technology is phase change memory, a more viable approach is this, in my opinion. You don't want to have only phase change memory as your main memory unless you want to give up performance unless you want to give up performance, basically. Basically, hybrid memory systems, you have one technology that we know well and that has good characteristics and that has some other bad characteristics, and you have some other technology that we know somewhat and that has some good characteristics and some bad characteristics, and you put them together. In DRAM, for example, if the goal is if it becomes very costly to scale, you may have very small amount of DRAM, but very large amounts of phase change memory. And if you can intelligently use that DRAM, then that's great, right? So we're going to talk about this, the hybrid memory technology. So I think a big challenge going into the future is, in addition to enabling a new technology, providing the best of multiple metrics with multiple memory technologies. So how do you do that? And I think that requires heterogeneity, configurability, and programmability. I think some of which we discussed before. Okay. I don't know what happened here. Authentication failed. Okay. So let's talk about hybrid memory systems a little bit. Actually, before we talk about hybrid memory systems, this may be a good time to take a break. Does that sound good? So let's be back at, let's say 20 past, 15 minutes.